What's up? Welcome to another video on linear algebra. So today we're going to be going over a pretty important section in linear algebra. It's called transformations. Now, transformations are basically what they are, what the names are. So in a transformation, you're going to have an x coordinate that's going to be corresponding to a y coordinate, and you've seen sort of transformations when you're dealing with functions. X is 1. So for every x component, you're going to have a y component. Right? And so basically the definition for transformation is just mapping. Right? So all we're doing is mapping. And what's interesting about this transformation is the premise of this is we're going from either a higher dimension to a lower dimension, or a lower dimension to a higher dimension. Okay, and once we start doing problems, you'll see, okay, I understand what he's doing, and I understand what's going on. Okay, so we're going to have a t, which represents the transformation, and it's going to be r to the n power, and it's going to go to r to the m power. So what do these mean? Well, the n is simply the column, and the m is the row. Okay, and your A is a m by n matrix. So our Rn will consist of column vectors, what we call them. So you have x1, x2, x3, x4, ... x to the n. So these are all n dimension. So the n is basically representing the column vector or subspace of column n. I think I'll write that down. Represents the column vector or subspace of column n. So let me give you an example. You'll have R2, which will basically have two components, right? If you have R3, you will have three components. R4, you guessed it, 25 components. Just kidding. It's going to have 4 components, right? That's all it's saying. And there's something actually, let's do that mapping thing. Wow. I know my iPad has to have some cool circle making device. Oh, genius. Okay. Pretty cool. Great circles. Okay, so Rm, we're going to transform these functions. So here, see, can I make that bigger? Oh my god, that's great. Okay, so in the Rn, we are going to have some x component where it's x1, x2, blah, blah, blah. And this will be your n column. And in the Rm, you'll have w vector, which is W1, W2, dot, 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 to WM. And this will be the M column. So one thing to know about this X vector is that the X vector has to equal the column number. And I think that's all the... Oh, one thing. Let's make it a different color. This W represents the codomain. Alright, and this X vector represents the domain. So the W is the codomain and the X is the domain. Okay? And when we're doing these problems, it's good to remember what we're basically doing here. And what we're basically doing here is we're going from different dimensions. So we'll go from R3 to R2, which is basically like saying 3D to 2D. And this is basically what Snapchat or any biometric device is doing, is that it's changing your face and taking all like the points on your face and making it into a 3D image, and that's how all the face filters work on Snapchat. So let's look up an example where we have an R3 and an R2. Oops. And we want to transform that. And we have this domain X vector, which is 1, 2, 3. And this codomain vector W with 14, 11. And so you want to transform this from R3, so R3 to R2. And your A is 1, 2, 3, 0, 4, 1. Which is a 2 by 3. So 2 row, 3 column. Okay, so I basically gave the answers already. So if we were to find the domain, what dimension is that? Well, it's in the third dimension. It's in R3. The codomain is in R2. The range is basically all the vectors in R2 that are mapped or quote-unquote paired. And the range is the subset which are parts or equal to the codomain. And I'll write that down. All the vectors in R2, which is here, in R2 that are mapped or paired, another way to say it, and the range is a subset codomain, the subset of codomain. So I guess another way of writing the range would be something like this. All vector so something like that. All right, so let's talk about matrix transformation. Matrix transformation is where T is a matrix and T of X is A times X. And we're going to see it used like this, where T sub A is R N, which is going to RM. So A was M by N, and the M are the, here we go. This is the M column, right? So you'll see after the transformation, that's the M value. So before the transformation is the N. So before that is the N. Okay, so let's go and do this. We have this 5 here. This 5 will be the N, and that 4 will be the M. So the T sub A will be R5 to R4, where R5 is the domain and R4 is the codomain. Perfect. Now only the column vectors get to be changed / mapped. Okay, so go ahead and do another problem. So we're basically trying to transform the X in some type of function, right? We're going from R3 to R2. Oops. Okay, so the domain will be R3, which is going to equal x1, x2, x3, and the codomain will be R2, which is the W1 and the W2. W2 like the taxes. Okay, so another problem where you're going to identify the domain and codomain. Well, here, x1 to 4 is going to be the domain, because that's going for from an R4 to an R2, as you can see, 2 coordinates. That's a codomain. Okay, so a new problem is being asked find the standard matrix for the transformation from R4 to R2. So we're going to go ahead and set up a matrix where it's 2, 3, -5, -1, 1, -5, 2, -3. And I've got those values from this system of equations above. And I'm going to have my x1, x2, x3, x4. Okay, so now is a good time to probably plan to foresee what you'll have after you multiply this. So what I mean by that is what n by m or n by n matrix will I have after I'm done multiplying. This is just a way to check. So if I look here at this left matrix, it's a 2 by 4 matrix, and this x vector is a 4 by 1, right? So since these are the same, they're the same, your new matrix that you'll get from the product will be a 2 by 2. 2 by 1 matrix. And that's exactly what you're looking for, because that's a two-dimensional coordinate or vector. So in this case, in this problem, they wanted you to find it for this x, where it was 1, -1, 2, and 4. So if we were to do this transformation with this x value, 2, 3, -5, -1, 1, -5, 2, -3 with that vector, it's going to spit out a -15 and a -2. So what you need to do is multiply and then add, right? So you take this row, multiply with that column, right? And then add them. So you get that for your answer. Okay, let's take a look at another problem where it says to find the standard matrix for transformation and use to compute t of this x vector and then check by substituting. So what we're going to do is we're going to construct our matrix, and this will be my x1 row column, my x2 column, and my x3. So if I look at this here, in my x1, I have 1, and x2 I have nothing, and x3 I have nothing of this x1. For my x2, I actually have nothing for x1. Now I'm looking at here. I have no x1s. I do have a 1 x2, and I have a -1 for the x3. And for this one, for the z, I have no x1s. I have 1 x2 and no x3s. That makes sense? Perfect. So that's my standard matrix. And now I'm going to check by substitution. So let's go ahead and see. But before I check, I guess I should point out that I acquired those values by using this, which is basically this, but over here. Okay, so checking, let's check. I have T105 equal to T105 equals to 10001 -1 010, which is a 3 by 3 matrix. And I'm going to multiply it to this 105 that it told me here. And that is a 3 by 1. So I should expect a 3 by 1 when I'm finished. And that's how I'll know I computed the multiplication correctly, right? By multiplying that, I get 1, -5, and 0. If you want me to do that multiplication, I will by pointing. So I'm going to take this row and I'm going to multiply that to this column. So 1 times 1 plus, I guess I'll write it down, 1 times 1 plus 0 times 0 plus 0 times 5. That's how you multiply, right? And then I got the Aw. And then I got the 1 here, because this equals 1. Okay. And you do that for the rest. And that's what you get. I'm sorry, this was not the checking part. This was actually doing the part. So what we did was we found the center matrix, and then we used this Tx that they gave us to compute it. And so we did. We got 1, -5, and 0. And by checking, we can directly substitute this x into the t here. Let's go ahead and try that. That's way easier. And I'm pretty sure it's a one-liner. Let's do it in yellow. So if I put 1, 0, 5 right into here, I'm going to get 1. And then x2 minus x3, that's 0 minus 5. And then x2, which is just 0. You can see I get a 1, -5, and 0, which is exactly the same thing we got here. So that checks out. Okay, so the next important thing that we're going to be doing is linear transformations. These are super important. So basically, you're going to have a u and a v, right? So there's 2 vectors, and they have to follow these 2 conditions, or 3. They have to be a u and v. They have to be 2 different vectors. So they also have to follow this addition, this vector addition condition, where if you add the u and u plus v and put it into the transformation, you would have to have them be able to pull out like this. If they can be in this format, that checks. They also have to be in this format, where if you multiply the k to the u, you can also take out the k, and it would still look the same. So after it meets those conditions, the matrix transformation is linear. Okay, so we want to show that t is linear, and it gives us this t first, but remember, we have to prove that it meets those conditions. So this is basically like my u, and this bottom one with the prime is basically like my v. So now what I'm going to do is prove that these conditions hold. And to be clear, this second line here, this quote-unquote v, I made that up. So they gave me this first one. They said, show that this t is linear. They gave me that. Then I said, okay, I need another vector that I can use to add to my u or multiply by some k term. So I created a new vector. This v, I created it. So you could do the same thing. Okay, so now let's do the addition one. Okay, so we're going to have t x, y, z plus x prime plus y prime plus z prime, x prime. And that's basically like we saw before, where this was my u and this was my v. So we're just trying to prove that, just to be clear. So that's going to equal t x plus x prime, y plus y prime, and z plus z prime. Okay. I'm sorry, I went a little ahead of myself. This is actually supposed to be x prime, y prime, z prime. Okay? Because I was looking at it differently. This here is my v vector, and then this here is my u vector. So I was basically saying this was u, and this was v. So that makes more sense. Okay, now from here, I could use that step that I was just about to make. I'm going to bring that over here. Okay, so that's that equals x plus x prime plus y prime. And then y plus y prime plus z prime. And then that's x plus x prime. And I'm going to point something out. I almost use a black color. You definitely will not see it on the black background. So if I look here, x plus y, that equals this t, this first t, right? So x plus y. If I were to move those together, but first let's see, y plus z, I have y plus z. And this x, I have that x. Y plus z, and then x. If I were to just pull those apart, I would essentially have x plus y, y plus z, and x plus x prime plus y prime, y prime plus z prime, x prime. So that is essentially the same thing as we have initially, plus t of x prime, y prime, z prime. So it's the same thing, right? So that checks out. So this idea of that the t of the summation of those two vectors will end up getting me this, the transformation of the u vector plus the transformation of the v vector. I have it here. So that checks out. Now I just have to prove that if I were to multiply it by some k constant, I get the same thing. So let's go ahead and do that. So if I have this, oh, wrong one. If I multiply that k in there, that's going to apply that to every single term. And then I'll get kx plus ky, ky plus kz, and then kx. And if I were to factor out a whole k from everything, I have x plus y, y plus z, and x. Well, that is simply k times t x, y, z. So that also checks out, and that means that t is linear. Ta-da! So t is linear. Let's try a problem where t is not linear. I think that'd be a great thing to see. So let's just say that we're given t xy is equal to x y plus 1. Okay, so now this is my, let's just say this is my u vector. I need a v vector. So I need another transformation coordinate. So I'm just going to say t of x prime y prime will equal x prime y prime plus 1. Okay, so let's try the first condition where we have to add the vectors. So let's say t xy plus x prime y prime. That's going to equal t x plus x prime y plus y prime. Okay, so that's also going to equal x plus x prime y plus y prime plus 1. But there's a problem, because t xy plus t x prime y prime, that's going to equal, let's see, x plus x prime y plus y prime plus 2. So as you can see here, we added the two vectors inside this transformation, and we were able to get x plus x prime and then y plus y prime plus 1. And then when we added them separately, we got x plus x prime and y plus y prime plus 2. And because they're not equal, and they're not the same, that indicates that it's not linear. So that's a case when it's not linear. So that is how you do the transformations. So that was a pretty interesting topic, but it's very important. So I hope that helped. If it didn't, leave me a comment and I'll go over more linear transformation problems or matrix transformations. So next video we'll do determinant and we'll explore that. So